Hello everyone, today we will study directional derivative. First of all, let me introduce what's directional derivative. Let f of sy be a two-variable function. Assume its graph z equal to f of sy has a smooth surface. Near sy equal to AB. Recall, the partial derivative f sub x of AB represent the rate of change in positive x direction. In positive x direction at xy equal to AB, and the partial derivative f sub y of AB represent the rate of change in positive y direction at the point xy equal to AB. Now, we define directional derivative in a similar way. Let V be a vector in the xy plane. Let V be a vector in the xy plane. The directional derivative dVf, the directional derivative d sub Vf of AB represent the rate of change at xy equal to AB in the direction of V. Next, we try to compute the directional derivative. Remember, when you compute f sub x, we compute the slope of tangent line in a cross section y equal to b. When we compute f sub y, we compute the slope of tangent line in a cross section s equal to a. Similarly, when we compute the directional derivative, we compute the slope of tangent line in the cross section passing through point AB in the direction of V. What does it mean, a cross section passing through AB in the direction of V? Let's look at the graph first. Let me show you a graph first. x-axis, y-axis, z-axis. Z equal to f of sy is the surface. It has a smooth surface near AB. Assume the graph looks like this. It could be any arbitrary graph. Assume the graph looks like this. Assume this graph represents a surface of z equal to f of xy. Point AB somewhere here in the xy plane. And let's assume that's the direction v. Assume that's direction v. A cross section passing through AB in the direction of v looks like this. A cross section passing through AB in direction of v looks like this. That's a cross section passing through AB in direction of v. F of AB somewhere here in the surface. That's f of AB. Next, we try to compute the slope of tangent line at f of AB. To find slope of tangent line, let's first of all pick point near AB in the direction of v. Assume this vector here is kv. K is a scalar. We don't know how long it is, so k is a scalar, but we know it points to the direction of v. So assume this vector is kv. K is a scalar. Then that's a point near AB in the direction of v. This point can be represented by AB plus KV. This point can be represented by AB plus KV. We don't know what V is. Let's assume V is V1, V2. Assume the component of V is V1, V2. Then this point AB plus KV AB plus KV can be rewritten as AB plus K V1 V2, K times V1 V2. That's AB plus KV1 KV2. That's A plus KV1 comma B plus KV2. So this point can be represented by A plus KV1 comma B plus KV2, and that's the point in the surface. The point in the surface is f of A plus KV1 comma B plus KV2. Next, we try to find the slope of secant line passing these 2 points. Next, I try to find the slope of secant line passing these 2 points. Slope of secant line. Slope of secant line is rise over long. Slope for any passing through 2 points. Slope passing through 2 points is always rise over long. Slope of a line passing through 2 points is always rise over long. The rise is distance between these 2 points. That's the change of f. The distance between these 2 points. The long is the length of the vector kv. The long is the magnitude of the vector kv. So slope of a line passing through 2 points is rise over run. Change of f, we use final point minus initial point. That's f of a plus kv1, comma b plus kv2 minus f of ab. That's change of f. And magnitude of kv, since k is a scalar, I can pull it outside. Since k is a scalar, I can pull it outside. I got absolute value of k times magnitude of v. Since we point in the same direction, we treat k as a passive constant. Since we are finding derivative in this direction, we treat k as a positive scalar. So absolute value of k is the same as k. We are looking for the rate of change in the same direction, so we treat k as a constant, is a positive constant. Otherwise, it points in the opposite direction. So k is a positive scalar. Absolute value of k is the same as k. That's the slope of the secant line. Then, in order to find the slope of tangent line, we take a limit. In order to find the slope of tangent line, we take a limit as k approaches to 0. As k approaches to 0, these 2 points will be very, very, very close. And the slope will be the slope of the tangent line. The slope of the secant line will be very, very close to the slope of the tangent line. When k becomes very, very small, these 2 points will become very, very close to each other. So the slope of secant line will be very, very close to the slope of tangent line. So when we take a limit as k approaches to 0, I get a slope of the tangent line. And this is the directional derivative. This is the directional derivative in the direction of v passing through point at x, y equal to ab. This is the directional derivative in the direction of v at s, y equal to ab. So that's the definition of directional derivative. This is the definition of the directional derivative. F of a plus kv1 b plus kv2 minus f of a b over k times magnitude of vector v. This is the definition of the directional derivative. At x, y equal to ab in the direction of v. The tangent line in the graph at s, y equal to ab looks like this. That's the tangent line. The directional derivative at AB in direction of V represent the slope of tangent line in the direction of V. This directional derivative represent the slope of the tangent line in the direction of V. Next, let's do some computation based on the definition of directional derivative. That's the definition of directional derivative. Suppose f of sy is differentiable at sy equal to ab, then the directional derivative of f at sy equal to ab in the direction of v is defined as this limit. Let's do some computation based on this definition. let f of sy equal to x squared plus sy. Find the derivative. Find the directional derivative of f at xy equal to 1, 2. In the direction of three, 4. So use definition. Directional derivative at 3, 4 f of 1, 2 is the limit, that's a vector, is the limit k approach to 0 f of a plus k v1, that's a, b, that's v1, v2. The point xy represents a, b, and the direction is v1, v2. We have 1 plus 3k, comma, 2 plus 4k minus f of ab, which is f of 1, 2, over k times the magnitude of the vector, magnitude of the directional vector, which is magnitude of 3, 4. Then simplify. We have k approach to 0 on the denominator. For magnitude of 3, 4, we can use Pythagorean theorem. Square root of 3 squared plus 4 squared, that's the denominator. On the numerator, I plug in 1 plus 3k for x. I plug in 2 plus 4k for y. And minus f of 1, 2. That's 1 squared plus 1 times 2. Then let's simplify. Take limit as k approach to 0. Let's simplify the numerator first. 1 plus 3k squared is 1 plus 6k plus 9k squared plus 1 plus 3k times 2 plus 4k, that's 2 plus 4k plus 6k plus 12k squared minus 1 plus 2 over k times square root of 3 squared plus 4 squared is square root of 25, which is 5. Take limit as k approach to 0. On the numerator, I combine like term. I get 21k squared plus 16k plus 3 minus 3 over 5k. Then cancel positive 3 and negative 3. Cancel k from top and the bottom. I have limit k approach to 0, 21k plus 16, which is, if I substitute 0 for k, I take limit, substitute 0 for k, I have 16. This number 16 means at the point 1, 2, in the direction of 3, 4, the rate of change is 16. At point 1, 2, in the direction of 3, 4, the rate of change is 16. This computation looks okay, but is there an easier way to compute a directional derivative? Is there an easier way? Let's observe the definition first. Look at this formula first. The term that looks most complicated is this term. The term that looks most complicated is this term. Can we find a formula to simplify this? Can we find a formula to simplify this? In this formula, we can see that in this expression, a and b, they are constants, that's a point. v1, v2 is also a constant that represents a component of a vector, they are also constants. In this formula, the only variable is k. So if I let g of k equal to f of a plus kv1, b plus kv2, then my g0, if I plug in 0 for g, for k, my g0 is, if I plug in 0 for k, my g0 is f of a comma b. If I let g of k equal to the first term, then my g of 0 will be in the second term. Then this directional derivative can be rewritten as limit k goes to 0, g of k minus g of 0 over k times magnitude of v. And since v is a vector, its magnitude is a constant, must be a constant. V is the directional vector, which is a constant vector, so its magnitude must be a constant. So this limit can be rewritten as limit k approach to 0, 1 over magnitude of v times limit k approach to 0, g of k minus g of 0 over k. And what's this? In first semester calculus, in your first semester calculus class, remember we define f prime of a equal to the limit x approach to a, f of x minus f of a over x minus a. Remember this formula in your first semester calculus? Limit x approach to a, f of x minus f of a over s minus a. If you try to match this formula and this formula, we can see that k represents x, 0 represents a, and denominator k minus 0 is k. So if you match this formula, we can see that k represents x, 0 represents a. So this is actually g prime of 0. So by matching a formula, we see that this limit is g prime of 0. By matching a formula, we see that this limit is g prime of 0. But what's g prime of 0? Let's compute g prime of 0. First of all, let's compute g prime of k, then plug in 0 for k. So what's g prime of k? We compute g prime of k using chain rule. G of k equal to f of a plus kv1, b plus kv2. Let the first component be x. Let the second component be y. Let x equal to a plus kv1, y equal to b plus kv2, then g of k can be rewritten as f of x, y. So g is a function of x and y, x is a function of k, y is a function of k. We can use chain rule to find the derivative. So g is the same as f. Use tree diagram. G is the same as f. F has two variables, x and y. In function x, the only variable is k. In function y, the only variable is k. Then, when we try to find g prime of k, we use chain rule. Delta f over delta x times dx over dk. X is a single variable function. Plus delta f over delta y times dy over dk. Delta f over delta x is f sub x of xy. Dx over dk. Take derivative with respect to k, I get v1. Delta f over delta y is f sub y of xy. Dy over dk is v2. That can be rewritten as f sub x of x. X is a plus kv1. Y is b plus kv2 times v1 plus f sub y of x. X is a plus kv1. Y is b plus kv2 times v2. Then let's g prime of k. For g prime of 0, I substitute 0 for k. So I get f sub x of a comma b, substitute 0 for k, times v1 plus f sub y of, if I substitute 0 for k, I have a comma b times v2. This can be rewritten as a dot product. F sub x of a b vector f sub x of a b, f sub y of a b dot v1 v2. This can be rewritten as a dot product. If you multiply dot product, you multiply first component to the first component, you get the first term. You multiply second component to the second component, you get the second term. So this can be rewritten as a dot product. And g prime of 0 equal to f sub x of a b comma f sub y of a b dot vector v. v1 comma v2 is the directional vector v. So the directional derivative dvf of a b, the directional derivative dvf of ab equal to 1 over magnitude of vector v times g prime of 0. 1 over magnitude of vector v times g prime of 0. And g prime of 0 equal to the vector f sub x of a b comma f sub y of a b dot vector v. And this can be rewritten as f sub x of a b comma f sub y of a b dot v over magnitude of v. This is scalar multiplication. This is regular multiplication. And this is dot product. For dot product, that's the formula says k times a dot b. That can be rewrite as, for dot product, k times scalar k times vector a dot b can be rewrite as ka dot b or a dot kb. That's why I can multiply the scalar to one of the vector. To make it easier, I multiply the scalar to the second vector. Then observe, what's this? What's this? This is the unit vector in the direction of v. This is the unit vector in the direction of v. This is the unit vector in the direction of v. This is the unit vector in the direction of v. So the directional derivative can be rewrite as dv f of a b equal to f sub x of a b comma f sub y of a b dot u, where u is the unit vector in the direction of v. And since u and v point to the same direction, this directional derivative can be rewrite as directional derivative in the direction of u, f of a b. Since u and v point in the same direction, they have different lengths, but they point in the same direction. Also, a and b could be any x and y values. Since a and b could be any x and y values, so the directional derivative can be rewrite as the directional derivative in the direction of u, f of sy equal to the vector f sub x of xy comma f sub y of sy dot u, where u is the unit vector in the direction of v. And this vector f sub x, f sub y has a name. It's called the gradient vector of f. This vector has a name. It's called the gradient vector of f. This vector has a name. It's called the gradient of f, denoted by an upside down triangle. It's read del f. It's read del f. That's called a gradient vector of f. It's read del f. It's read del f. It's read del f. So del f is always the vector formed by partial derivatives. So the directional derivative of function f in direction u can be rewrite as gradient of f dot u. That's the formula, where u is the unit vector in the direction of v. Del f is the gradient vector of function f. That's the simplified formula for directional derivative. In addition, this formula also works for functions with 3 or more variables. If f has 3 variables, gradient of f is the vector of f sub x f sub y and f sub z. If f has n variables, gradient of f is f sub x1, f sub x2, up to f sub xn. This formula works for functions with n variables. The proof is very similar as the proof for two variable functions. Now, let's redo the previous problem using the new formula. First of all, we find the unit vector in the direction of v, which is 3, 4. So the unit vector in the direction of 3, 4 is, you take 3, 4, the vector 3, 4, divided by its magnitude. The unit in the direction of 3, 4 is, you take 3, 4, vector 3, 4, divided by its magnitude, which is 3, 4 divided by, use Pythagorean theorem for denominator, we have 3 squared plus 4 squared. 3, 4 over 5, which is 3 fifths, 4 fifths, 3 fifths and 4 fifths. That's the unit vector in the direction of 3, 4. Then we find the gradient vector. Next we find the gradient vector. F sub x is 2x plus y. If I substitute plug in the point 1, 2 for xy, if I plug in 1, 2 for xy, I have 2 times 1 plus 2, which is 4. Next, for f sub y, I take derivative with respect to y. I get x. If I substitute the point, if I substitute sy equal to 1, 2, I get 1. So the gradient vector at 1, 2 is the vector 4, 1. So the directional derivative at the point 1, 2 is gradient vector dot unit vector, which is 4, 1 dot 3 fifths, 4 fifths. Then apply dot product, I have 12 over 5 plus 4 over 5, which is 16 over 5. The answer is the same, but using this formula, we have less computation than the old formula. So we know that directional derivative tells us the rate of change at point A, B in different directions. In point A, B, the directional derivative tells you the rate of change in different directions. And we know that in general, the directional derivative is different in different directions. The value of the directional derivative is different in different directions. The value of the directional derivative is different in different directions. Can we find out in what direction the directional derivative has the maximum value? Can we find out in what direction the directional derivative has the maximum value? Let's observe the formula first. The directional derivative of function f at a, b in the direction of u is the gradient of f at a, b dot the unit vector. This is a dot product. For dot product, there's a formula says that equal to magnitude of the gradient f at AB times, this means multiplication, this is dot product, this means multiplication, times magnitude of u times cosine theta, where theta is the angle between these two vectors. Since we try to find out in what direction the directional derivative at AB has the maximum rate of change. So at point AB, the gradient vector must be a constant vector, so its magnitude must be a constant. And we leave unit vector vary. We try to find out in what direction the derivative has the maximum rate of change. So we leave u as a variable. But u is a unit vector. U is a unit vector. Its magnitude is always 1. And as the direction change, cosine theta change. Theta is the angle between these two vectors, between u and the gradient vector. Theta is, as u change, angle theta change. But we know cosine theta varies between -1 and 1. Cosine theta varies between -1 and 1. So its maximum value is 1 for cosine theta. Its maximum value is 1. Cosine theta equal to 1. This occurs when theta is 0. Cosine theta equal to 1 when theta is 0. When theta is 0, u must point to the same direction as the gradient vector. When theta is 0, u must point to the same direction as the gradient vector. So, in the direction of gradient f of AB, that means u has the same direction as gradient f of AB. The directional derivative at AB has the maximum value. The directional derivative has its maximum value. And its maximum value is what's its maximum value? When u has the same direction as the gradient vector, angle between two vectors is 0. Cosine of 0 is 1. 1 times 1 is 1. 1 times a constant is the constant itself. So that's the maximum rate of change. The maximum value of the directional derivative is magnitude of the gradient vector at AB. And we can write this conclusion as a theorem. Suppose f of sy is differentiable at sy equal to AB, then the maximum value of its directional derivative the maximum value of its directional derivative at AB, at point AB is the maximum value of its directional derivative at point AB is the magnitude of the gradient vector at AB, and it occurs, this maximum occurs when the directional vector u has the same direction as the gradient vector at AB. And similarly, this theorem also works for functions with 3 or more variables. This function also works for functions with 3 or more variables. Let's look at an old example again. Let f of sy equal to x squared plus xy at sy equal to 1, 2. In what direction does f has the maximum rate of change? And what is the maximum rate of change? So, first step, we find the gradient vector at 1, 2. First of all, we find the gradient vector at 1, 2. Partial derivative is 2x plus y. Substitute the point for x and y. I get 2 times 1 plus 2, which is 4. F sub y. Take partial derivative with respect to y. I get x. Substitute the point for x and y. I get 1. So the gradient vector at 1, 2 is the vector 4, 1. According to the theorem, in the direction of 4, 1, f has the maximum rate of change. Which means the directional derivative in this direction has the maximum value. The directional derivative has the maximum value in this direction. And second question asks, what is the maximum rate of change? According to the theorem, the maximum rate of change is the magnitude of the gradient vector. Maximum rate of change is the magnitude of the gradient vector at 1, 2, which is the magnitude of 4, 1. Use Pythagorean theorem, find the magnitude, that's square root of 17. If we compare this answer with the directional derivative in the direction of 3, 4, we can see that directional derivative in the direction of 3, 4 is 16 over 5. And the directional derivative in the direction of 4, 1 is square root of 17. Square root of 17 is more than 4. And 16 over 5 is 3.2. We can see that this is larger than this directional derivative, because this is the maximum rate of change, which is the maximum value of the directional derivative. It's larger than the directional derivative in any other directions. It's larger than the directional derivative in any other directions. Let's look at another example. Let f of sy equal to 3x squared minus 2y squared at negative 3 over 4, 0, find the rate of change toward point 0, 1 at -3/4, 0. In what direction does it has the maximum rate of change? And what is the maximum rate of change? So let's do part A first. For part A, we are looking for the directional derivative. First of all, let's find the direction first. What's direction V here? What's direction V? From one point, we're looking for the rate of change toward another point. This is vector V. From one point, we are looking for the rate of change toward another point. That's vector V. To find vector V, we use head minus tail. To find vector V, we use head minus tail. From one point toward another point, this is vector V. To find vector V, we use head minus tail. So vector V is 0 minus -3/4, 1 minus 0, which is 3/4, 1. Next, we try to find a unit vector in the direction of V. Next, we try to find a unit vector in the direction of V. So I first of all compute the magnitude of V. Magnitude of V, we use Pythagorean theorem. Square root of 3/4 square. Square root of 3/4 square plus 1 square, which is 9/16 plus 1. That's 25/16 under square root, which is 5/4. That's the magnitude. Then to find a unit vector, we take vector V, divide by its magnitude. Vector V is 3/4, 1, divided by its magnitude. Magnitude is 5/4. Then we have 3/5, 4/5. That's unit vector U. Then we compute the directional derivative using partial derivatives. Then we compute the directional derivative using partial derivative. We first of all find f sub x. F sub x is, we take partial derivative with respect to x. I have 6x. Take partial derivative with respect to y. I have -4y. Then substitute. Substitute the point. Substitute the point -3/4, 0. We start from this point. You must substitute -3/4, not the other one. We start from this point, -3/4, 0. That's the starting point. We must plug in the point, the initial point, -3/4, 0. So if I plug in, I have -6 times -3/4, which is -9/2. If I plug in 0, I got 0. So the gradient vector, it should be lowercase f. The gradient vector at f, gradient vector of f at -3/4, 0 is -9/2, 0. Then the directional derivative in the direction u of f at -3/4, 0 equal to the gradient vector at -3/4, 0 times the unit vector, which is -9/2, 0 dot 3/4, 3/5 5 4/5, which is -27/10. -27/10. That's part A. Part B. Next question, part B. At the point -3/4, 0, in what direction does it has the maximum rate of change? And what is the maximum rate of change? When the direction is the same as the gradient vector, at the point -3/4, 0, the directional derivative has the maximum value. So for part B, in the direction of -9/2, 0, in the direction the same as the gradient vector, the function has the maximum rate of change. And the maximum rate of change is the magnitude of the gradient vector. And the maximum rate of change is the magnitude of the gradient vector. And the maximum rate of change is the magnitude of the gradient vector, which is which is 9/2. That's the maximum rate of change. Next, let's look at some interpretation about gradient vectors. Look at this theorem first. Let f of sy be a differentiable function, and let f of sy equal to k be a level curve of function f. Then for all point P on the level curve, the gradient vector at P is always perpendicular to the tangent line. Here, f of sy is a differentiable function. That means its graph must be a smooth surface. F of sy equal to k is a level curve of function f. So a level curve looks like this. Assume that's a level curve, f of sy equal to k. Since f of sy has a smooth surface, then its level curve must be a smooth curve. The theorem says, for all point P on the level curve, the gradient vector at point P is always perpendicular to the tangent line. Suppose that's the tangent line at point P. This theorem says the gradient vector at point P is always perpendicular to the tangent line. Suppose that's the gradient vector. It must always be perpendicular to the tangent line at point P. That's what the theorem says. Let's prove it. Let's prove the theorem here. Proof. Since the function f of sy is differentiable, then the level curve its level curve f of sy equal to k must be a smooth curve. If a function is differentiable, its graph must be a smooth surface in 3D. Then its level curve must also be smoothed. So the level curve, since it's smoothed, it can be traced by a differentiable vector function. R of t. R of t has two components, x of t and y of t. Since the level curve is smoothed, it can be traced by a differentiable function, r of t. R of t has two components, x of t and y of t. Since this curve is traced by this vector function, that means this vector function must satisfy the equation of the level curve. Hence, f of x of t comma y of t must equal to k. That means if I plug in x and y into this equation, it must satisfy this equation. So f of x of t, y of t equal to k. Next, I'll try to take derivative for this equation. I'll try to take derivative for this equation. Take derivative on both sides of the equation. If I take derivative on the left side, this is a function inside function. We need to use chain rule here. Function f has two variables, x and y. X has a variable t, y has a variable t. When I take derivative with respect to t, I use chain rule here. I have delta f over delta x times dx over dt plus delta f over delta y times dy over dt. On the other side, k is a constant. If I take derivative, I get 0. Then this derivative can be written as a dot product. I can write it as gradient of f over delta x, comma delta f over delta y, dot ds over dt, comma dy over dt equal to 0. This is the gradient vector. And this is r prime of t. dx dt is x prime of t, dy over dt is y prime of t, so that's r prime of t. If the dot product of two vectors is 0, that means they must be perpendicular vector. So gradient f must be perpendicular to r prime of t. And here, r prime of t is called the tangent vector of the vector function, which is also the directional vector of the tangent line. Next, let P be a point. Assume the coordinate is x0, y0. Let P be a point on the level curve. F of sy equal to k. And let r of t0 equal to x0, y0. That means at point P, the x and y coordinate are x0, y0. And a vector function at point P, t must be t0. Then, at point P, I can plug in x0, y0 into the gradient vector. And I plug in t0 into the tangent vector. Then the gradient vector must be perpendicular to the tangent vector at point P, since they are perpendicular everywhere. This is the gradient vector at point P. This is the tangent vector at point P. Tangent vector represents the directional vector of the tangent line. So that's the directional vector of the tangent line at point P. And they are perpendicular to each other. Let me show you in the picture. Assume at point P, the coordinate is x0, y0. That's a tangent line. That's a tangent line. The directional vector of a tangent line is the tangent vector. Tangent vector is here. That's r prime of t0. That's a tangent vector. If the gradient vector is perpendicular to the tangent vector at point P, then the gradient vector must be perpendicular to the tangent line itself at point P. If the gradient vector is perpendicular to the tangent vector at point P, then the gradient vector must be perpendicular to the tangent line itself at point P. So the gradient vector at point P is perpendicular to the tangent line at point P. Let's complete the proof. And this theorem says, if f is differentiable, then for all points on a level curve, the gradient vector is always perpendicular to the tangent line. Next theorem, let f of s y z be a differentiable function, and let f of s y z equal to k be a level surface of function f. Let C be a smooth curve lies on a level surface. Then, for all point P on C, the gradient vector at P is always perpendicular to the tangent line at P. Here, since f of s y z is a differentiable function, then all its level surface must be smooth surface. Let me first of all show you a smooth surface first. Assume this smooth surface represents a level surface f of s y is equal to k. Assume this surface represents a level surface f of s y z equal to k. It's a smooth surface. Let C be a smooth curve lies on the surface, on the level surface. Suppose C is a smooth curve lies on the level surface. Then the theorem says, for all point P on C, the gradient vector of f is always perpendicular to the tangent line at P. Suppose that's tangent line at P. And that's the gradient vector of function f at P. That's the level surface f of s y is equal to k. This is a gradient vector of f at point P. The theorem says, for all point P on curve C, the gradient vector is always perpendicular to the tangent line at P. Let's prove it. Since C is a smooth curve, then it can be traced by a differentiable vector function. R of t. Here we have three components. Since C is a 3D curve, we have three components: S of t, Y of t, Z of t. Since C lies on the level surface, is C light on the level surface. F of SYZ equal to K. That means this vector function must satisfy this equation. This vector function must satisfy this equation. So when I plug in SYZ, I must get this function equal to K. Then when I plug in SYZ, I have f of x of t, comma y of t, g of t equal to K. Next, I take derivative with respect to t. I take derivative with respect to t. So I have f of x of t, y of t, z of t equal to the derivative of k. On the left side here, f is a 3-variable function, and x is a function of t, y is a function of t, z is a function of t. Here we can use chain rule for the derivative. F has 3 variables, x, y, z. X has a variable t, y has a variable t, and z has a variable t. If I use chain rule here, the derivative is delta f over delta x times dx over dt plus delta f over delta y times dy over dt plus delta f over delta z times dz over dt. On the right side, derivative of constant is 0. Then here I can write the left side as a dot product. It can be written as delta f over delta x, comma delta f over delta y, comma delta f over delta z, dot ds over dt, dy over dt, dz over dt, they equal to 0. This is the gradient vector of f. This is gradient vector of function f. This is the tangent vector r prime of t. This is the tangent vector r prime of t. If their dot product is 0, that means these two vectors must be perpendicular. So the gradient vector is perpendicular to the tangent vector. Next, let P be a point. Assume the coordinate is x0, y0, and z0. Let P be a point on C. And let R of T0 equal to x0, y0, z0. That means at point P, t equal to t0. Then at point P, gradient vector of f at x0, y0, z0 is perpendicular to the tangent vector at t0. The gradient vector at x0, y0, z0 is perpendicular to the tangent vector at t0. This is the gradient vector at P, at point P. This is the tangent vector at T0. Tangent vector is the directional vector of the tangent line. So that's the directional vector of the tangent line. At point P. Let me show you the picture. Assume at point P, the coordinate is x0, y0, z0. That's the tangent line. That's the tangent line. And this is the directional vector. This is the directional vector at point P. That's r prime of t0. here we can see that if the gradient vector is perpendicular to the directional vector of the tangent line, then the gradient vector must be perpendicular to the tangent line itself. So, since the gradient vector at point P is perpendicular to the directional vector of the tangent line at point P, so we can say that at point P, the gradient vector is perpendicular to the tangent line. At point P, the gradient vector is perpendicular to the tangent line. Let's complete the proof. And this theorem says, if f is a differentiable function, then for all smooth curves on the level surface, the gradient vector is always perpendicular to the tangent line at all points on the curve. Next theorem, let f of syg be a differentiable function, and let f of syg equal to k be a level surface of function f. Then for all point P on the level surface, the gradient vector at P is always a normal vector of the tangent plane at P. Here, f of syg is a differentiable function, and f of syg equal to k is a level surface of function f. Let me first of all show you the graph of the level surface. Since function f is differentiable, then its level surface must be a smooth surface. The level surface must be a smooth surface. Assume that the level surface f of syg equal to k. Then the theorem says, for all point P on the level surface, the gradient vector at P is always a normal vector of the tangent plane at P. So let P be a point on the surface, on the level surface. This theorem says, the gradient vector at P is always the normal vector of the tangent plane at P. So let's prove it. Assume the coordinates of point P is x0, y0, z0. So that point P equal to x0, y0, z0 be a point on the level surface f of syg equal to k. And let C1 and C2 be two smooth curves. Which lie on the level surface. Passing through point P. Assume C1 and C2, they don't tangent to each other at point P. Assume they don't tangent to each other at point P. When two curves tangent to each other. For if two curves tangent to each other at point, that means they share a tangent line at this point. Here we'll try to use two different tangent lines to find a normal vector. So we assume these two curves, they don't tangent to each other at point P. Since we try to use two tangent lines to find a normal vector, we assume the curve C1, C2, they don't tangent to each other at point P. When two curves tangent, they share the same tangent line. We try to use two tangent lines to find a normal vector. So let C1, C2 be two smooth curves on the surface, on the level surface, passing through point P. Assume they don't tangent to each other. Let's call this curve C1. Call this curve C2. They are both smooth curves on the level surface, passing through point P, and they don't tangent to each other. Next, I want to show you the relationship between tangent line and tangent planes. Let me first of all show you tangent line first. How does the tangent line looks like? Suppose we have a curve. And the curve is smooth at point P. How does the tangent line at point P looks like? In order to find tangent line, we keep zooming in. When we keep zooming in toward point P, the curve passing through P will tend to a straight line. And this straight line is the tangent line at point P. So let's zoom in at point P. If I zoom in at point P, if I zoom in toward point P, the window looks like this. This line looks straighter than this line. If I keep zooming in, if I zoom in again, if I zoom in again toward point P, the window looks like this. This line is even more straight than this line. Then if we zoom in again, toward point P, we will have an almost straight line passing through point P. That's a new window. Here we have an almost straight line at point P. So we can see that as we keep zooming in toward point P, the curve passing through P tends to a straight line. And this straight line is the tension line at point P. As we keep zooming in, we can see that the curve tends to a straight line, and this straight line is a tension line at point P. Next, let me show you the tension curve, the tension plane. How the tension plane looks like. Suppose we have a smooth surface. Suppose we have a smooth surface. Let P be a point on the surface. How the tension plane looks like? So same thing, we keep zooming in toward point P. Then the surface will tend to a flat plane. If we keep zooming in toward point P, assume this is a smooth surface, the surface will tend to a flat plane. And this flat plane is the tension plane of this surface at point P. So let's zoom in toward point P. If I zoom in toward point P here, the plane will look flatter at point P. If we zoom in toward point P, the plane will look flatter toward point P. Then if we keep zooming in again, toward point P, then the surface will be even more flatter. If we keep zooming in toward point P, the surface will be more flatter. As we keep zooming in, this surface that passing through P will eventually be a flat plane. And this flat plane is called a tension plane at point P. Tension plane of the surface at point P. So we can see that here as we keep zooming in, toward point P. The surface passing through P tends to a flat plane. And this flat plane is a tension plane. It's a tension plane of the surface at point P. As we keep zooming in toward point P, the surface passing through P tends to a flat plane. And this flat plane is the tension plane of the surface at point P. Now let's try to draw tension line and tension plane together. Suppose we have two curves here. Suppose we have two curves passing through point P. Call this C1. Call this C2. Then when we zoom in toward point P, this line will be straighter. This is C2. This is curve C1. As we zoom in, we can see that this curve will be straighter. This curve will be straighter. As we keep zooming in toward point P, the curve will eventually tend to a straight line. Here we can see that as we keep zooming in toward point P, when the surface tends to a flat plane, these two curves will tend to two straight lines. And the thing is, no matter how we zoom in, these two curves always lie on the surface. So when the surface tends to a flat plane, these two curves will tend to two straight lines that lie on the plane. Which means the tangent line of these two curves lies on the tangent plane at point P. So here we can say that if P is a point on a smooth surface, then for all smooth curves on the surface, passing through P, the tangent line of the curve at point P always lies on the tangent plane of the surface at point P. If there's a point on a smooth surface, then for all curves on the surface passing through P, the tangent line of the curve at point P always lies on the tangent plane of the surface at point P. Keep this idea in mind, and then let's go back to the theorem. In the theorem here, C1 and C2 are two curves on the surface passing through point P. So their tangent lines are both lie on the tangent plane at point P. Suppose that's the tangent plane. Then their tangent lines must both lie on the tangent plane at point P. Their tangent lines are both lie on the tangent plane passing through point P. Let's call this tangent line L1. Then we call this tangent line L2. Then both L1 and L2 will lie on the tangent plane at point P. Since both lines lie on the tangent plane, their directional vector also lie on the tangent plane. Since both tangent lines lie on the tangent plane, their directional vector also lie on the tangent plane. So let L1 be the tangent line of curve C1. Let L2 be the tangent line of curve C2. Let V1 be the directional vector of line 1. Let V2 be the directional vector of line 2. So in the proof here, since C1, C2 are smooth curves on the surface, then we know that their tangent line must both lie on the tangent plane. So here we can say that, so their tangent line lines with directional vector v1 and v2 both lie on the tangent plane. Both lie on the plane which tangent to S at point P. Hence we can say that V1, V2 both lie on the tangent plane. Hence V1 and V2 both lie on the tangent plane. According to the previous theorem, the gradient vector at point P is perpendicular to both tangent lines. According to the previous theorem, the gradient vector at point P is perpendicular to both tangent lines. Hence, we know that the gradient vector of f at point P, the coordinates x0, y0, z0, must be perpendicular to both v1 and v2. So here, let me show the gradient vector in the picture. This is the gradient vector of f at x0, y0, z0, which must be perpendicular to both v1 and v2. Now let's go back to the proof here. Since curves C1, C2, they don't tangent to each other at point P, then their tangent line won't be parallel at point P. Since curves C1 and C2, they don't tangent to each other at point P, then their tangent lines won't be parallel. Hence, they are directional vectors. Hence, the directional vector of the tangent line won't be parallel. So V1 won't be parallel to V2. Then, by a theorem in 10.4, we know that if a vector is parallel to two non-parallel vectors in a plane, then this vector must be the normal vector of the plane. Here we know that the gradient vector here is perpendicular to both v1 and v2, and they are non-parallel vectors in the tangent plane. Then the gradient vector here must be the normal vector of the tangent plane. Therefore, by the theorem in section 10.5, since v1 and v2 are two non-parallel vectors in the tangent plane, and the gradient vector is perpendicular to both vectors. Then the gradient vector at x0, y0, z0 must be the normal vector of the tangent plane. At point P. So the gradient vector of f at x0, y0, z0 must be the normal vector of the tangent plane at point P. Now, before we complete the proof, I see a mistake here. In this proof here, all letter f must be lowercase f. Because the function is lowercase f, all letter f here must be lowercase f. So that's the complete proof for this problem. And also keep in mind that in this theorem here, the gradient vector of function f at point P is always the normal vector of the tangent plane at point P. Next, let me show how to find the equation of a tangent plane to a surface. Equation of the tangent plane to a surface. Let S be a surface in R3. Suppose S can be represented by an equation. Suppose S can be represented by equation f of x, y, z equal to k. Then S can be considered as a level surface of F. Suppose function f is differentiable at point P. Where point P has coordinates x0, y0, z0, where point P is a point on surface S. Where point P with coordinates x0, y0, z0 is a point on surface S. Then, by the previous theorem, we know that the gradient vector of function f at x0, y0, z0 is the normal vector of the tangent plane at point P. Now, for equation of a plane, we know that the equation of a plane is a times x0, x minus x0, plus b times y minus y0, plus c times z minus z0. A tangent plane is a plane, so we can use equation of a plane to find the equation of the tangent plane. In this equation, a, b, c represent the coordinate of the normal vector. Here, for this tangent plane, the normal vector is the gradient vector of function f at x0, y0, z0. So the component of the normal vector is f sub x, f sub y, and f sub z at point x0, y0, z0. That's the component of the normal vector. Now, do we know a point on the tangent plane? Do we know a point on the tangent plane? P, here P is a point on the tangent plane, and the coordinate is x0, y0, z0. So the coordinate here is x0, y0, z0. That's the coordinate of point P. X minus x0, y minus y0, and z minus z0. That's the equation of the tangent plane. Next, let me introduce the normal line of a surface. A normal line of surface S at point P is the line perpendicular to the tangent plane. At point P, passing through P. A normal line of a surface S at point P is the line perpendicular to the tangent plane at P and passing through the point P. Let me show you the picture here. Suppose that's the surface S. S can be considered as the level surface of a function f of x, y, z equal to k. Let P be a point on the surface S. Let P be a point on the surface. Assume that's the tangent plane at point S. That's the tangent plane of S at point P. Assume that's the tangent plane of S at point P. A normal line is a line passing through P, perpendicular to the tangent plane. That's a normal line. A normal line is a line perpendicular to the tangent plane and passing through point P. This is a normal line. Since the gradient vector of function f at point P is the normal vector of the tangent plane, then the gradient vector of function f at point P should be the directional vector of the normal line. So the gradient vector of function f at point P should be the directional vector of the normal line. Now let's try to write the equation for the normal line. We know the equation of a line is always r of t equal to r0 plus tv, where r0 is a point on the line, v is the directional vector of the line. Here we know that a point on the line is point P. Coordinate of point P is x0, y0, z0. Coordinate of point P is x0, y0, z0. So that's a point on the line. The directional vector is the gradient vector, and we know that the component of the gradient vector is f sub x, f sub y, and f sub z. Then add them together we have x0 plus tf sub x, comma y0 plus tf sub y, comma z0 plus tf sub z. If we distribute t and add the vectors, that's R of t. Then we can write each component by itself. S equal to x0 plus tf sub x, y equal to y0 plus tf sub y, z equal to z0 plus tf sub z. That's the equation of the normal line passing through point P. That's the equation of the normal line of surface S passing through point P. Let's look at this example. Find the equation of the tangent plane and normal line of the elliptic paraboloid. Z equal to 2x squared plus y squared at the point 1, 1, 3. We are looking for the tangent line and normal line. First step, rewrite the equation of the surface. Make it equal to 0 first. We have 2x squared plus y squared minus z equal to 0. Rewrite the equation of the surface. Make it equal to 0 first. Then set this equal to the function f of s, y, z. Set this equal to the 3 variable function f of s, y, z. Then next we take partial derivative with respect to x, y, z. Next take partial derivative with respect to s, y, z. Take partial derivative with respect to x is 4x. Partial derivative with respect to y is 2y. Partial derivative with respect to z is -1. Then we plug in the point x0, y0, z0. Plug in the point x0, y0, z0. I get 4, 2, -1. That's the gradient vector. So the gradient vector is the vector 4, 2, -1. Next, equation of the tangent plane is f sub x, x minus x0 plus f sub y, y minus y0 plus f sub z, z minus z0 equal to 0. Then f sub x is 4, f sub y is 2, f sub z is -1. Then the point is 1, 1, 3. X minus 1, y minus 1, and z minus 3. x0, y0, z0 represent a point 1, 1, 3 equal to 0. Then we can simplify 4x plus 2y minus z minus 4 minus 2 plus 3 equal to 0. Usually we bring a constant to the other side. 4x plus 2y minus z equal to positive 3. That's the equation of the tangent plane. Now for equation of the normal line, we use the formula x equal to x0 plus tf sub x, y equal to y0 plus t times f sub y, z equal to z0 plus tf sub z. So plug in s, y, z. x0, y0, z0 is the point 1, 1, 3. The gradient vector is 4, 2, -1, which is the directional vector, which is the direction of the line, plus 4t plus 2t minus 1t. This is the equation of the normal line. Tangent plane, normal line.